Hello guys, my name is Adrian and welcome to my channel. If you are new to the channel, I'm trying here to create a small framework in order to be used for some game that I'm developing live on stream. In the previous video, we talked about matrices. We talked about the translation, the scale, and how by using those we can move and, let's say, shrink an object into this 3D world that we are trying to build. If we are looking right now at our geometry, it seems that it's a little stretch. We have a square where all the edges are equal. We have a square in terms of the geometry, but on the screen, we are seeing a little stretch. It is because our width of the window is higher than the height of the window. So how are we fixing this? Some smart guys from the, let's say, math university or I don't know where, they invented this type of functions or this type of operations that are calling projection, that are working, of course, with the matrices. And most of the time we have two projections. And of course, these are the, let's say, most used one in games in general. You have the orthographic projection, which is something that is used very heavily for 2D games in general, and the perspective, which is the one that is very used for the 3D games. Today we'll try to implement both of them. What I'm trying to say to you first is that it's not this type of projection, these types of, let's say, calculations that are done behind those functions or those operations. It's not something that I invented. It's something that you can find on the internet. Today I will just implement it in my framework and I will use it to make this square look like a square. So the first thing that we will do for sure, we will go into the shader in here and we will kind of do something like projection multiplied by the view multiplied by the model. What I can tell you, this is the projection. This will be some matrix that will have some certain values in their structure. This will be the view. It will be the matrix that will hold the position where we are looking from. And of course, because when you are looking at some object, you can have also something like an orientation. So the view matrix, most of the time, it's holding also the orientation. We are not using the scale in general for the view, but maybe there are some exceptions. So projection matrix will hold the projection. We'll start with the orthographic. We'll finish with the perspective one. The view will hold the position of the viewer and the orientation, and the model, like before, it was the matrix that will hold the rotation, scale, and position of the object. If we're running right now, we should not see anything on the screen. Okay. So first, let's try to fix that. We have the camera matrices that we are sending, and what we can do here first, because we are not using them, that's the problem. We didn't create something like a matrix for the, let's say, for the view and something for the projection. So what we can do easily is like mat4, and we'll have something like view, okay, and we'll have some mat4 for the projection. Okay, and in here, of course, we can have, and we need to be very careful with the order, so we can have view and projection. So we are sending the view and the projection. If we are sending right now, if we are running the project, everything should be back to what it was. Why? Because we are using in the, let's say, the order of the operations. Of course, it's very important, but we are using some matrices that are the identity matrix. Like I discussed in the previous video, those matrices are just the default version. So we are not applying any projection, we are not applying any view. So the result should remain the same. So what we can do first? First, what I want to do first, it's the follow. I will start by going into the command, into the math, and for the mat4, I will add a new function called ortho, for example, which comes from the orthographic projection. So for it, we'll have a float left, a float right, float bottom, float top, float near, and floor. Okay, so left represents the left corner of the screen, right, the right, bottom, top, and so on. These are just some coordinates that map the entire viewport. Okay, the near and the far represents, let's say, the something they are called also planes. Okay, something called clipping planes. So whatever it's in, let's say, in front of the near value, it will be drawn, and whatever it's beyond far, it will not. So whatever it's in front of the near, it will not be drawn, and what is in front of the far plane, it will be. So this is something you can imagine, something like a camera that zooms and so on. It seems like if, for example, if you're kind of having the camera, you can imagine that whatever is in front of the camera, of course, it's not recorded. Okay, so that's value. You can imagine it as a value that it's before the near value. So let's generate this function. So, like I said, the magic for it is on the internet. You can find it. If you're curious more about the, let's say, the math explanation of it, it's not that hard to understand. You can have on the internet some nice pictures and so on. I don't want to have pictures here to not get into the copyright and any other weird shit. So what we can do, first we need to remember that we are using columns to represent our matrix. Very, very, very important. Okay, very important. So first, what we'll take in consideration, we will need to adapt some values that are on the identity on the diagonal. Let's say we need to take care first of the element x, or the first element in the first column, the second element in the second column, and the third element in the third column. So what we are doing, columns 0, like I said, the first element is x. What we are doing, we are having a 2.0 float, and we divide it by the right value minus the left. After that, something very similar happens with the second element. But for the second element, we are using the top minus bottom. For the columns 2, or the third column, z, we are using a minus 2.0, okay, and we are using the far minus near. Why the minus? It's because of the axis. In OpenGL, the z, it's like in front of you. It comes, if you are looking, let's say, in the 3D space, the z will be the axis that will come to you. The x will be in the right, and the positive y will be in the top. So that's why the minus, okay? So this is what we need to put for the first 3 elements. After that, what we need to adjust, it's the, let's say, not the position. I will not say to want the position, but we need to adapt the last column. It's something that we have also in the position of the, let's say, in general, in the translation, you see we are affecting the last column, but we need to do it. So we'll have columns 3, and we'll have the x equal with something. Let me have something like this, y and z. And what we are having? We are having minus, and first we are starting with right plus left, and we are multiplying by the right minus left. We are having the same with top plus bottom, okay, and we have top minus bottom, and the same applies to far plus near and far minus. What I can tell you, this let's say order of operations are very important. What I can tell you also, these are a little different than the matrices for Vulkan. when we implement Vulkan in our engine, in our framework, we will need to redo something about here that will be like specific for Vulkan. Okay, why? Because OpenGL works with these planes between -1 and 1. But Vulkan works with, and DirectX also, works with the plane from 0 to 1. So when we will kind of do something about Vulkan, we need to adjust this matrix in order to support the Vulkan operation that needs to have the clipping between 0 and 1, not -1, 1 like OpenGL. So let's make all this constant. Like I said, if you're curious, you can go a little on the internet to read more about the orthographic matrix. Very important. And yeah, that's pretty much everything. Let's go into the main. And if we are going here into the projection, we can have something like ortho. But what I will do today, because in general, you have, let's say, 2D graphics, which are using, let's say, sprites, which use the real values of a PNG, for example, like you are working with things like 100 by 100 and so on. But our geometry here is now like 0.5 and so on. If we are using the orthographic like we're supposed to, with the, let's say, the width and the height and all that stuff, we will not see anything on the screen. Not because it will not be correct, it will be because the geometry will be very small. But I will do something that I learned from GLFW. In one of their examples, they have some computation like this. So, auto, of course, we need to have an aspect ratio. Aspect ratio that will be used later on for, let's say, also the perspective. But first, I think what we need to do, we have already width and height. Okay, that's good. We need to have something like this. Okay, just a second. And we need to have something like window width and window height, of course. Window height. Let's align a little the stuff here. And what I will do for the orthographic part, it will be something like this. In general, you have something like 0, window width, 0 window height, -1, 1. Or even window width, 0, and -1 and 1, if you want kind of to invert the y coordinate. But what we will do today, it will be something like this, minus aspect ratio. Okay, the second one, it will be the aspect ratio, and we'll have a -1.0 and 1.0. And at the end, we are keeping -1 and 1. Let's try and let's see what we will get. So right now, if you are seeing, we are having our square, our quad that looks normal, and doesn't matter if we are resizing the window, it will still look the same. Of course, we are still not applying any change from the window. That will be very useful for the perspective, but we will not implement it today, the resizing. But you see right now, with some just math, our object doesn't look stretched anymore. What I would like to do right now, I would like to go into my matrix and declare another type of orthographic projection. One that is a little more simple. So we'll have something like ortho, and we'll have the left, we'll have the right, we'll have the float bottom, and we'll have the top. And at the end, of course, the void. This doesn't take in consideration the near and the far. Why? I want to use this, let's say, matrix, this type of a matrix, when my depth doesn't matter. So if I'm doing some 2D game, I'm not having depth. Okay, I don't want to have, for example, for the UI, I'm not interested about the depth, I don't have layers and so on. The first type of matrix that I've showed you, it is very useful when you want to use something like layers and so on. But for example, for the UI, I will not use it. So what we are doing first, we are copying the first like we had it before, but instead the right minus left, the top minus bottom remains the same, but instead of -2 and the far near, we're pointing -1.0. If you remember, minus like this, because we are want to take in consideration the z-axis, which is with minus in our case. Good. And other than that, we are just going and copy, paste the last column. It should remain, because it's z, it should remain as 0. So let's make this constant. And let's, of course, test it. So if I'm removing the -1, 1, which are what we are using in OpenGL in general, like I told you about those clipping planes, if we are removing that and we are just running the code, we should see the same result. So it's the same result. Let's say less computation done, and I will stick with this one for now. Okay, now we talked about the 2D, is the orthographic projection. Let's implement also the perspective one. Why not? But before we are doing that, we need to kind of implement a new class or a new set of functions, not especially a class, which we'll call it functions. In these functions, of course, we'll have the math namespace. The same applies for the source file. Let's put the functions in here, and we'll implement 2 functions. Okay, we'll not have a class. If we want, we can have a class like class functions and so on, but I will like to implement it just as simple as some C functions. So we'll have the first one, auto. We'll call it radians. Okay, and we'll have float degrees. Okay, or you can have like radian and degree if you want to keep it like in a singular. So it will return a float. Another one, it will be auto tan. It'll have a float value, or it can be also a degree, because it's a but the whole idea is not, it's kind of needs to expect this to be let's say in a radians. So this tan will be the tangent of an angle, okay, but the angle needs to be in radians. So first we need to implement the conversion, because most of the time we know to work with the normal degrees that we learn in school, but in the 3D worlds we are working with radians. So we are having this on just a second, float. So let's have, for example, here just a value, or we can call like radian. Okay, and let's implement these 2 functions. For the first one, I will just go on the internet and copy some value. Okay, so what is a radian? We are having here like a return of a degree multiplied. You see the AI already completed, but I will want to have a shorter version. So it's mostly like something around 100 degrees multiplied by p or something like this, and it will you will get this value. So multiplied by your degree, you will get the angle in radians. Okay, and for the data tangent, we'll use just something that std tan, and we'll use this radian. Okay, why I kind of put this under some function is because maybe in the future we want to replace it with something else, and it will be much easier just to change it here, and it will be the same everywhere. Now, into the headers, of course, let's include the functions. Very simple. And we will start to declare a new method, auto perspective. and we'll have the float FOV, field of view. We'll have the float aspect, which will be aspect ratio. We'll have the float near and float far. This is the same as this, is like the near plane and the far plane. It has the same mechanic, like whatever it's in front of the near, like a value that it's smaller than the near, it will not be drawn or not be, let's say, in this projection matrix. And whatever it's beyond the far will not be also taking consideration. And for the perspective first, we need to do something like we need to have a constant auto, A for angle, we'll have something like radian, and we transform the field of view in radian. So after that, we need to have this tangent, which will be A, we'll have a T, where we'll have the tan, okay, from the tangent. We put our angle, because I told you, needs to be in radians, and we multiply it by 0.5, which is kind of similar with the division by 2. After that, we are having an R, which is the ratio between far minus near. Not the ratio, sorry, more like a range. Okay, so we have far minus. And the same, we are doing this. So columns, 0, just a second, x equal with the 1.0 multiplied with the t multiplied with the aspect. Like I told you, this information is on the internet. For me, I'm not a very mad guy. It's maybe probably much harder to explain to you. So if you want to, I'm just showing you how to implement it correctly. If you want to kind of go on the internet and read more or see more for yourself, you are very allowed to do that. So for we are talking about right now, we are trying to modify this and this, okay? And after that, we'll modify this. So first, like for every projection, we are starting with the first 3 elements on the diagonals, okay? So for the second one, like I said, we are doing something like this. After that, columns 2, Z, and very important, like the minus here is very important on the third element on the diagonal. So we have a minus, far plus near, multiplied, sorry, not multiplied, divided by the range, which range is far minus near. After that, for the W, very important, minus 1. After that, columns 3, Z equal with the minus, and here we'll have 2.0 multiplied by the far, multiplied by the near, okay, and divided by the range, which the range is far minus near. And very important, the last element in the matrix, like this one, is to be 0. Okay, if I'm trying to take this, for example, I will comment this situation. So I will have something like, for example, the AI already completed for us. So I will try to have 45. Okay, I will have the aspect ratio, the 0.1 for the near plane and 100 for the far one. What we need to do also, if we are running right now the code, we will not see anything on the screen. Why? Because when we are using the perspective projection, the view matrix is very important. So when you are using perspective, you need to use the view matrix and you need to move your viewpoint, because otherwise our object is in the center, in the 0.0, okay, in the center of the screen. We are trying to see something starting from the center of the screen, and that's why our object is something, let's say, not in the field of view. It's like in the, like I told you, is between your, say, with codes like between your eyes and the camera. So what you need to do, it's something to have a view, and you need to take the view and to translate it 0.0, just a second. So it will be like 0.0, and we'll have a minus 3.0f, which will kind of step a little back with our camera. So if we are running right now, we should see as before. So right now we are using a perspective. This is used mostly for the 3D games, and the orthographic is used for the 2D. I will stick for now with the, or we can keep the 3D for the next tutorials. This implementation for the projections, or let's say matrix projections, it's very important because you can see that the square, it's like normal now, not stretch anymore. And by having this, now we can start and having concepts like cameras, like the view, and so on. And I think this is it for today. If you're new to the channel, this is a good chance. We will continue our journey. We will discuss about the textures, frame buffers, and so on. At some point, we will discuss about lighting, and we'll tackle also the 3D part in our framework. And from now on, the live streams should be more often because we are kind of, let's say, we have the minimum instruments that can kind of let us to build a game. And yeah, that's it for today. Thanks for watching. Thanks for being here, and see you in the next video. Bye bye.